Welcome to Summarize Science. Today, we are looking at a major breakthrough in AI transparency called LLMSurgeon. Think of large language models like digital alchemy, where the ingredients are massive piles of internet data. However, these training recipes are often kept as some of the most guarded secrets in the tech world. Knowing what an AI read during its training is crucial for understanding its biases and potential failures. Until now, most tools could only check if a single specific document was in the training set, not the overall balance of topics. The researchers have now formalized a new process called data mixture surgery to solve this macro-level problem. The goal is to estimate the broad categories of data used, such as computer code, scientific papers, or web articles. LLMSurgeon operates as a detective, operating in a rigorous three-stage pipeline shown here. Crucially, it does not need to peek inside the AI's private weights or code to perform this audit. Instead, the tool looks at the text that the target AI generates in response to neutral prompts. The core idea is that an AI's output statistically reflects the proportions of data it was fed during its pre-training phase. This allows the researchers to treat the recovery of the mixture as a distribution matching problem. But there is a catch. Simple classification tools often get confused between similar types of text. For example, a classifier might struggle to tell the difference between a research paper and a Wikipedia article, creating a blurred prediction. To fix this, LLMSurgeon uses what is called a calibrated soft confusion matrix to understand exactly how its own classifier makes mistakes. By solving this as a mathematical inverse problem, the tool can deblur the observations and find the true training mixture. This mathematical correction is the key to achieving high fidelity without needing direct access to the training data. To prove the method works, they created a benchmark called LLMScan using open-source models with known training recipes. The results shown in this table prove that LLMSurgeon is significantly more accurate than previous methods. On general-purpose models, it achieved overlap accuracies as high as 95%, far surpassing traditional counting methods. The researchers also found they could track how these internal mixtures change and stabilize as an AI is being trained over time. This graph shows the trajectories of domain estimation error throughout the training process of different models. It reveals that while training can be volatile in the middle, the models eventually converge to a stable composition. They even tested the tool by injecting toxic data into a sandbox model to see if LLMSurgeon could find the hidden mass. Remarkably, the tool was able to recover a monotonic estimate of the toxic training mass with very high precision. This means researchers can now audit models for harmful data or copyright risks entirely from the outside. Let's recap the most important takeaways from this research. First, LLMSurgeon allows us to recover the digital DNA of an AI without needing voluntary disclosure from tech companies. Second, it uses smart math to correct for the confusion that standard classification tools often face. Third, it provides a vital window into the black box of modern technology for the purpose of safety and governance. In the future, this could lead to mandatory auditing of AI models to ensure they are built on fair and unbiased data. It might also help authors and creators identify if their work was used to train a model without their permission. As AI becomes a bigger part of our infrastructure, tools like this are essential for a trustworthy future. Thanks for watching Summarize Science.